discussing the IV characteristics of a transistor, we are taking NPN transistor in the circuit, and the characteristics are basically identical with slight differences in for CB circuit, CE circuit and CC circuit. And because for various reasons common emitter circuit is most widely used. So, we are taking the characteristics of the CE circuit. We said earlier that these characteristics can be divided into three parts. We discussed the saturation region, in which both junctions are forward biased, emitter junction as well as collector junction is they both are forward biased, and this is the cutoff region. To go below IB equal to 0, that means in the other direction we will have to change the polarity of this as it is shown here, and this will make even this is the p type base connected to the negative terminal of the battery. So, even input junction is reverse bias. So, this region is called cutoff region, where both the junctions are reversed bias, and as I have said that saturation region and cutoff region, they represent two states, quite different states, and they are very useful for digital circuits in which the transistor is used as a switch. Now, the third region, that is above IB equal to 0 and on the right side of this saturation region, this is called the active region. In active region, this is called active region. Most useful. Active region is where the emitter junction is forward biased and collector junction is reverse biased. Emitter junction is forward biased and collector junction is reverse bias. And this is the polarity which we use when we want to use the transistor as a amplifying device. So, actually active region is very important for the amplifying for a amplifier circuit. Now, here we will notice that as we increase the input current, the output current is changing. For larger values of input current, corresponding output current is high. This is what is expected in the amplifying circuit, that output current should vary proportionally to the input current, and only the magnitude should change. And here we are seeing that this magnitude is in milliamperes, while this is in microamperes. So, this is definitely a amplified output, and in fact, we can find out several useful parameters from here. So, active region, emitter junction is forward biased, collector junction is reverse biased, and for amplifier, for an amplifier, the active region is to be used. What does it mean? at the moment we are talking about the DC, but as I have said, in amplifier our purpose is not to just amplify the input signal, but a AC signal, because whether the audible sound or the radio frequency signals, these are all AC signals of different frequencies. For audible frequencies these are in kilohertz, but radio frequencies can be very high. So, our purpose will be to amplify a AC signal. Now, once we fix a circuit and fix in the sense that what is the DC output current and what is the corresponding input current, this is to be chosen for the circuit, and then over that we have to superimpose the AC signal. So, choosing the AC output current, DC output current and input current, this is called Q point. We will talk in details about this choosing the operating point and in the next section. So, when we have chosen the input current, for example, in this case equal to 40 microampere, and the corresponding output current will be roughly 4 millimeter for this particular transistor for which these characteristics have been drawn. Now, when we apply the AC signal, that will change, that will this input current will vary and correspondingly the output current will vary. Now, in no part of the cycle when the AC is superimposed over these DC, the operating point, at no part the signal should go beyond the active region on either side. That means, it should remain within this prescribed region, and here the because any portion which falls, if by wrong choice it touches or it comes in the saturation region, the output will be distorted, because that much part will not appear in the output. So, output will be a distorted signal that we have to avoid. Same thing will happen if the signal moves in the cutoff region, because in cutoff region the net output current will not be the function of net input current. So, that will be distorted. Hence, signal when superimposed is still for the whole cycle, the operation should continue to remain within active region. Now, these characteristics prove very useful. One is, if we are asked to find the current gain beta for the circuit, we can find from here. We take any input current and how much is the corresponding, or we change the input current by this much amount, how much the collector current change, then we can find from these output characteristics that beta will be equal to change brought in the collector current by change in the base current. This we can find out. Also, because these two quantities they pertain to the output circuit, hence the slope is totally that will give the output impedance or output resistance of the circuit. From the slope of these curves we can find the output impedance, resistance, output resistance or output impedance of the circuit, that can be easily be determined from these characteristics. Few more points we note down from these characteristics is that if we look these regions, actually here this is the crowding of these characteristics. For example, for next 20 degree rise, this may be like this, where this will have less space as compared to this. Now, this is to be explained. So, 2 points I explained. Number 1, when we increase the base current, then why there is a crowding of these curves. This crowding arises because this is high injection. High injection, when the input current is very high, it is called high degree of injection. The lot of charge carriers will be injected into the base. As a result of this, the gain falls. Gain falls, and gain is, for example, beta change in IC by change in IB. If this falls, then the ratio will be less, and this will not change corresponding to that. Here the gain has fallen, and so it is not much as it was here because of high injection. So, they come closer. This is one reason. And other point is actually we have said that these collector junction is reverse bias, and if we look at that potential energy diagram, this is N P N, then this is reverse bias, and all the electrons which are crossing the base region, they are collected here. So, what we have said earlier, that should amount that the output current should be independent of this reverse voltage. This is true to a very large extent, but not 100%. There is a finite curve, that means there is a slope, and they are not exactly flat, and this is because when we increase this reverse voltage here, when this reverse voltage is increased, as I have discussed earlier, that there will be a broadening of the depletion width, and because base is very lightly doped, so more penetration of the depletion region will be in the base region, and hence that lesser number of electrons will recombine, giving rise to slightly higher value of collector current because of the with the rise in this reverse bias voltage. That is why there is a slight rise in the current with voltage. Had it been totally independent, then these curves should have been totally flat, but I have shown that there is some slope, and that is because of what we call the base width modulation. With the rise of reverse voltage, the depletion width falls. With the rise of the reverse bias, depletion width falls. So, lesser number of charge carriers will recombine and the current will slightly rise. So, that explains these characteristics. We can get the current gain, we can get the output impedance from this circuit, from the slope itself, and these are very useful characteristics. So, that covers the input and output characteristics of the transistor. The significant thing which we have said is that the output characteristics, which are more important, that they can be divided into three parts: the saturation part, the cutoff part and the active region. The saturation and cutoff regions are used when we design digital circuits, and transistor is being used in the two states. One is the conducting state, the other is non-conducting state. This is what in actual switch we have. Even in simple electrical switch, the up and down, in one case there is a high conduction through the switch, in the other case there is high insulation. So, this is equivalent to that, but for amplifying purposes we have to use the active region, and we should choose the operating point properly, so that over the whole AC cycle that nowhere the signal goes near the saturation region or the cutoff region. We will talk more about this operating point soon. Now, having said so much, we now talk about some features which are important in designing a circuit, in handling the currents and voltages in a circuit, and we have broadly not talked about these points yet. So, some important parameters and phenomena. First is punch through. Punch through. If we keep on increasing the reverse voltage, a situation may come, these dimensions are very small. This whole dimension of the transistor is a fraction of a millimeter, or is around a millimeter, which contains three regions: the emitter region, the base region and the collector region. Then there are ohmic contacts, and this makes our transistor. If we go on increasing this voltage, how our output characteristics will change? These output characteristics for very large values of the reverse voltage at the output. I just take out of these several curves, I pick up one, and this will happen this way. This is VCE, this is IC, and this is the normal curve, normal operation. It is supposed to be restricted, the operation should be restricted to this region, but if we keep on increasing, then the depletion width keep on increasing, and a situation may come that we will find that the collector current will rise suddenly. This is the breakdown, actually breakdown, and we are not supposed, this is prescribed what is the value of VCE max for each number. This is provided by the manufacturer. So, this is called punch through. That means, the depletion region is almost touching the collector electrode, and the transistor action ceases. Transistor action, which is fundamental for the transistor, continues till we have the three regions: the emitter region, the base region and the collector region. When the voltage at the collector junction goes beyond a certain limit, then there will be a sudden rise in the collector current, and this is known as punch through, in which the depletion region has spread to such an extent that it is almost touching the collector electrode. This is punch through, and the manufacturers prescribe the value of this VCE maximum which we are supposed to observe. The second point is also related with this depletion width, that is reach through. Reach through, this is because base region is already very small, very thin, and it is lightly doped. So, when this voltage is not large enough yet, but is still large enough so that the penetration of depletion region is there, and this depletion touches almost the emitter region. That means, base will cease to exist. You followed here. This is the base, and because this is lightly doped, so more spread of the depletion region will be in the base region, and this situation may come when this depletion region almost touches the emitter. When this happens, transistor again stops working, and this is known as reach through process. Third is in this category base spreading resistance. Base spreading resistance, and it is written by R B. Base, this is base, it is a thin region, and it becomes thinner because of the spread of the two depletion regions. It is thin, and then it becomes thinner because of the spread of the depletion regions, and the doping level is also very light, very lightly doped region, and hence it offers a resistance, and resistance to the passing currents, and that is known as base spreading resistance. And the value of this base spreading resistance R B is of the order of 100 ohms. I hope you have understood what is the meaning of base spreading resistance, what gives rise to base spreading resistance. Base spreading resistance comes from the two factors, that the base is narrow, it is a very small thin slice, and doping is low. So, three factors contribute to this. The base is thin slice, so the dimensions are very small. Doping is very light. What does doping do? By doping, we change the resistivity of the semiconductor, and so it is directly related with the doping level, and doping is kept very low in the base region for the reasons which we have discussed, what are the requirements for a efficient transistor. And third point which contributes to this is that the base is thin, and thickness of base further declines due to the spread of depletion region, particularly the base collector region. So, these are the three factors which contribute to this base resistance, base spreading resistance, which is of the order of 100 ohms or so. In many analyses we will disregard it, we can neglect it considering other points, but there are situations, as we will see, where this resistance cannot be neglected. So, base spreading resistance. And then next point is variation of beta, the current gain with temperature and the collector current. Beta is one of the most significant parameter for a transistor. This we have been repeatedly saying, and because beta represents the current gain in a common emitter circuit, in common emitter 99% circuits are common emitter circuit, common base circuits have very few applications, and common collector is of course sometimes used, but most widely used circuit is common emitter, and beta is connected with the common emitter circuit, it is the current gain. So, let us see how does it vary with the temperature and collector current. With collector current, this is beta, this is collector current IC, and initially beta increases, attains a constant value and then falls, and this fall is, as I have said, when we try to explain the crowding of these output characteristics, that high injection, when very high injection of charge carriers is there from the emitter, then collector is unable to handle them as efficiently as in this region. So, there is a fall in the value of beta, and this fall may be significant. This, if it is 100, this may be 75 and even low. So, this is how the current gain beta varies with the collector current, the output current. Another variation is with respect to temperature. Transistor contains semiconductors which are very sensitive for current the temperature variations, and because of that there is a change. If this is the plot at a temperature say at 20 degrees centigrade, then about 100 or so this variation will be like this. Current gain beta changes with collector current, output current, and it also changes with change in temperature, and with rise in temperature beta increases. Now, I have been very frequently talking about the changes in temperature. Let me make this point clear here, that temperature, ambient temperatures, we know in winter and summer it changes, and changes of the order of 50 degrees are quite common. Plus, when we change the place in Kashmir area, in hilly areas, in Himalaya, in Himachal Pradesh, in winter the temperatures and temperatures in summer in Delhi, there is a drastic variation. So, that is why in all operations temperature variation is important. Another points which contributes, when we are talking about a circuit, is concealed in a box for example, then because of various currents and voltages and components like a transformer and other devices, there is heat generation. That heat changes the environment of the device under which it is operating. You must have seen that your TV set, your radio set, your cassette, after say use of say 15-20 minutes, if you touch it from outside, it has become hot, it has gained certain temperature and 20-30 degree rise because of those electrical operations. It is quite natural. So, temperature is a significant parameter in all these variations. Then finally, in this category we talk dependence of this voltage base emitter junction. Here if this was, then this voltage, this also varies with temperature for the same reasons that semiconductor, the resistivity falls with temperature. So, with the rise of temperature VBE also falls, and it has been calculated, observed experimentally, that roughly VBE falls at the rate of 0.2 volts for every 10 degrees rise. For you it is sufficient to remember that temperature also changes the voltage drop which occurs between base and emitter junction. So, these are certain parameters which we will be making use. Now, we go for another thing very important, AC equivalent circuit. Circuit for transistor. What is the equivalent circuit and why do we need these 2 points? Let me make very clear at the start. The transistor which we have been discussing, this is used for example in a amplifying circuit. We have to analyze the circuit. Trial and error is not the best policy. A circuit designer will prefer to have a model and what are the requirements which we expect from the circuit, and that will fix different circuit elements which are to be used. What is the amount of current, what is the amount of voltage, which resistances are to be used in the circuit, that he should know. So, there should be a way to analyze the circuit. AC equivalent circuit. Why AC? Because in amplifiers we are interested in amplifying AC signals, and so AC equivalent circuit is required. Now, what is this actual equivalent circuit? And then we will come to certain simplifications which are possible under certain situations, and then we will see that how these derived equivalent circuits can be used for the analysis What is the analysis? We should be able to calculate what will be the voltage gain in the circuit, what will be the input impedance, what will be the output impedance, what is power gain, what is the current gain in the circuit. All this will be possible through proper analysis, and a proper analysis needs a proper equivalent circuit. So, that is why we have to talk about this. Now, this is the circuit. Now, we are talking of AC equivalent circuit. So, there will be AC input current with this small letter and small this alphabet I, we note AC emitter current. Similarly, there will be AC collector current. And AC base current. And that relationship holds, that this, as the DC emitter current was divided into two parts, one goes to the recombination in the base region, which gives rise to base current, and the other gives the collector current. That continues. Similarly, this AC emitter current will be split in the two, and this relation still holds, as we have written for DC case I E I C plus I B. This is for DC direct current, and for AC case we can write a similar relation. So, this still holds, and in many situations, as we will see, that in transistor analysis, because the base component is or at least 2 orders of magnitude is smaller than this. So, in many situations I C will be equal to I E. This we will see when we come to this point, and here this is base, this is collector, and this is emitter. Now, here this is R B. What are these components? Let me first try to explain that. C E prime, this is the emitter junction capacitance. Emitter junction capacitance, and R E prime, this is the dynamic resistance of emitter. R B base spread, we just talked about the base spread, base spreading resistance, and C C, this is collector junction, capacitance, and this is R C prime. R C prime is the collector AC resistance. So, this is emitter junction capacitance, collector junction capacitance, this is dynamic emitter resistance, this is the effective the collector AC resistance, and this is the base spreading resistance. So, if any circuit in any circuit, if the transistor is replaced by this equivalent model, this is exact model, this is exact, then we should be able to compute the properties of interest. But we can simplify this. Here we can simplify this, and the simplified equivalent circuit which we will be using is this. This is the simplified model for transistor. Here we have dropped, for example, this resistance, the collector resistance. Collector junction is a reverse bias junction, and RC is to the tune of in megohms, very high resistance, and because it is in parallel, so this can be taken almost as open. Similarly, this capacitance, these two capacitances can be dropped when the operation is limited in frequency, that means up to few tens of kilohertz or say up to 100 kilohertz. We can, the impedances offered by these capacitances are very high, and because they are in parallel, so they can be neglected. So, as long as our operation is limited to this range, which of course again is not very rigid, because it varies from transistor to transistor. There are transistors which will go still higher in frequency, but normally we will be using them in this range, and for that this simplified model is good enough. Here these are the currents IC, IE and IB, and IC is equal to IE, and this resistance, how we get dynamic resistance, that I can show you, that how practically we can get the value of this emitter dynamic resistance, dynamic of the emitter. Experimentally we can find it from these input characteristics of the transistor at a fixed value. We know that this is the characteristic, this is IE, and this is VEB, the voltage between the emitter and base, and this is the how the current exponentially increases. Here we take the operating point somewhere here, and we take the changes this much change in this voltage VEB changes the current by this amount, the ratio of the two gives you R E prime. E B we can write actually E B at a fixed value of VCE. This is how the dynamic resistance of ammeter is defined. It is written either as R E prime or many times it is written just as R E, and instead of determining it experimentally, we can find out by a simple equation. It can be shown that R E prime is equal to 26 millivolts when I E, the ammeter current, DC ammeter current, is in milliamperes. So, this is most widely used expression for finding the dynamic ammeter resistance. 26 divided by I E, the DC ammeter current. When DC ammeter current is expressed in millivolts, then this gives the resistance in the in ohms. This is, I am sorry, this is also in millivolts, this is also millivolts. So, we get the resistance in ohms, and this resistance varies from 10 ohm to 50 ohms. So, this is about the model, and we will use this model. Let us take an example that how we can find out the three currents in a circuit. The three currents are the collector current, the ammeter current, and the base current. Let us consider this simple circuit. This is an example. For example, we have seen here that to find out the value of this dynamic resistance, we need the value of ammeter current. So, I am taking a general example to demonstrate that how simple it is to calculate the three currents I C, I B and I E in a circuit when some parameters are given, and what is given is that in this circuit VBE is 0.7 volts, and also given that beta, the transistor current gain, is say 50, and we have to find out the value of these three currents. Then there is another point which needs emphasis, is this example illustrates that what are the kind of resistances which are to be used in a small circuit, in small low power circuits small signal circuits with which we are mostly concerned, and what are the battery voltages, what are the resistances. So, this is the reason behind this example. Now, if we apply Kirchhoff's voltage law, popularly known as KVL, Kirchhoff's voltage law, which is the summation of voltages in a closed loop. If we write the equation, then we will get this is the summation. Here there is a current IB. So, the voltage drop here is 43 K. K is actually I can replace this with 10 to power minus 3, but when we take the resistances in kilo ohms, often they are left like that, and then the currents will be in milliamperes. If we take it in ohms, if I replace it with 10 to power multiply by 10 to power 3, then the currents will be in ampere, and because ampere is a large current, normally we will encounter with milliampere current. So, this is good enough to maintain this in the kilo ohms. So, this equation is to be solved for IB. Here 5 volts and 43 K IB, and this is given as 0.7 volts. So, we substitute and we get IB equal to 44.3 volts divided by 43 K, and that gives 0.1 milliampere. So, base current is 0.1 milliampere, and IC we can find out. IC we know is beta times IB, because beta was defined as the ratio of these two currents, output current by input current. So, here we can use this relation in this form, very widely used in transistor circuits, and this is 50 into 0.1 milliampere. So, this is equal to 5 milliampere, and then the IE, for the determination of IE we use the relation IC plus IB, and we have found out these two currents. So, we can get the value of emitter current. This is 5 milliamperes plus 0.1 milliampere, and that gives you IE, the emitter current, to be 5.1 milliampere. This further shows that IC was 5 milliampere. So, IC is always less than IE, but they are very close. This is 5.1, this is 5. So, our assumption, which we will be very frequently use in the analysis of these circuits, this is valid. So, I have taken this example to illustrate few things. Often we will be required to calculate the currents. So, how to calculate the currents in a circuit, and then another purpose was to show you that what kind of resistances, what is the order of resistances which we have to use in transistor circuits. So, here this was the base resistance normally written as RB, and this was the collector resistance with the collector, which is written as RC, and what are the batteries which are used in the circuit. So, I am sure that it has added to your knowledge and how to handle these circuits. This is simply one example we have taken. The next thing which we will be considering, how to choose the operating point, how to choose the operating point, and what is the meaning of operating point, that we will see, and then design of biasing circuits. So far we have been using very primitive approach. For example, here I have used 2 batteries, and soon when we take these 2 topics, we will see that single battery will do the job, and then what are the points, what are the features, what are the considerations in choosing a appropriate operating point, that we will have to see in the next lecture.